Hi, my name is Olivia Lanes, and welcome back to Quantum Computing in Practice. This is episode 2, Quantum Circuits. We're going to be covering several topics in today's lecture, but what I want you to walk away knowing are the following 3 things. 1, what IBM quantum computers actually are, so that you at least have a rough picture in your mind of what you're doing when you send a job to one of those over the cloud. 2, what Qiskit is, what primitives are, and how we can use them to create and execute quantum circuits. We'll also discuss at a high level the different types of IBM quantum processors available and what distinguishes one from another. And 3, lastly, the typical workflow that we follow to run experiments at scale. This includes selecting the best primitives for your use case, mapping a problem to a quantum circuit, and applying error suppression and mitigation, which enable us to squeeze as much power out of these machines as possible. Now, there's a lot of information here, but stick with me, because soon enough we're going to put it all together in the context of some real examples. First, let's briefly discuss qubits and the actual quantum hardware. As an experimentalist, I can promise you that it is fascinating, and it really helps connect the dots to visualize what's actually happening when jobs are sent to a quantum computer through the cloud. The processors that we're going to be using are built with superconducting transmon qubits. Here's what a small IBM Quantum processor looks like. Now, these small squares here are the qubits themselves, so there are a total of 5 on this chip. The transmon itself is a capacitor, and it consists of 2 plates of metal hooked up in parallel with a nonlinear inductor called the Josephson junction. But to see the Josephson junction, you actually have to zoom in even more. It's created from 2 overlapping layers of superconducting metal, and where the 2 pieces overlap and touch is the junction. A Josephson junction is an element that can be used to create an artificial atom with multiple energy levels, and we isolate the bottom 2 energy levels as our qubit state. The squiggly lines here represent the microwave resonators, basically 2D transmission lines coupled to the qubit. Now, when we program a gate, that essentially equates to choosing a highly calibrated microwave pulse, and the specific frequency, amplitude, shape, and duration of those pulses make the qubit do specific things. The instructions for the microwave pulse go from your computer to the cloud and then are read and interpreted by room temperature control electronics, which take those instructions and physically generate the pulses. We call them microwave pulses because they all fit within the microwave frequency bandwidth, which is around 1 gigahertz. After the room temperature control boxes create the pulses, they travel through the cables into the dilution refrigerator and eventually to our quantum chip. The signal goes into the resonators through a wire bond on these pads, and then it flows down the transmission line into our qubits. Now, I know this all might have been a little technical, and these details aren't crucial to understand for us going forward, but I hope now that you can all at least picture the physical system that you're all about to interact with. So where do these quantum computers actually exist? Well, IBM has dozens of quantum computers all around the world, and we've recently upgraded our fleet to contain only 100 plus qubit processors, as I mentioned in the previous lesson. Some of them are located in an IBM Quantum data center in upstate New York. Those systems are deployed all over the cloud for everyone's use. And some of them are dedicated on-premise systems, complete with all of the electronics to make them work, that support our partners in the IBM Quantum network. Now, let's talk about Qiskit, which is IBM's open source software development kit designed to work on quantum computers. From now on, I'll be referring to this as the Qiskit SDK. There's also the Qiskit ecosystem, which is a collection of software tutorials and functions that build on or extend the core functionalities of Qiskit, as well as Qiskit Runtime, which is a quantum computing service and programming model that allows users to design and efficiently execute their quantum workloads by using Qiskit primitives. And a primitive is basically a small building block that you can use to design larger circuits or a job. The 2 primitives that are most important to us are going to be the sampler and the estimator, which we'll discuss in more depth shortly. If you haven't downloaded and installed the Qiskit SDK yet, there is no time like the present. Qiskit 1.0 was recently released, and it's more performative and stable than ever before. So for those of you that are just getting started, you came in at the perfect time. For those of you that are already familiar with Qiskit, you'll need to download and reinstall the newest version. We recommend using pip to install Qiskit and Qiskit Runtime and running them through a Jupyter Notebook in a web browser of your choice. So you're also going to need to install Jupyter Notebook or Jupyter Lab. In case you haven't done that already, these tools are all free, and you can get them up and running on your own local machine without any cost. Make sure to add Qiskit with the visualization option dependencies so it works with Jupyter and lets you plot things. You will also need to set up a virtual Python environment, and there are instructions on how to do this on the Qiskit install page linked here. Once you've become familiar with Qiskit and you're ready to run jobs on real quantum computers, you'll need to register at quantum.ibm.com and create an IBM Quantum API token. And there is also a link here for that. A detailed walkthrough of how to do this, follow all the instructions in our documentation page like I mentioned, or you can watch the Coding with Qiskit installation video here, both of which are linked and in the description. Now we're just about ready to start talking about quantum circuits. Since the point of this course is to teach you, the audience, how to scale up your jobs to be run at a 100+ qubit scale, I believe the most constructive way forward is to first consider the overall workflow that we're going to follow. And the easiest way to understand a typical quantum computing workflow is through Qiskit patterns. Qiskit patterns are a conceptual framework allowing users to run quantum workloads by implementing certain steps with modular tooling. This allows quantum computing tasks to be performed by powerful heterogeneous computing infrastructure. These steps can be performed as a service and can incorporate resource management, which allows for seamless composability of new capabilities as they are developed. Here are the main steps, which experienced Qiskit users will likely already recognize. The first step is mapping. This step formalizes how we take a general problem that we're interested in and figure out how to map it into a quantum computer in the form of a circuit. Next, we optimize. In this step, we use the Qiskit transpiler to route and lay out the circuit onto an actual physical quantum hardware. This includes translating the individual quantum gates into sequences of operations that are performed on the hardware, as well as optimization in the layout of those gates. Next, we will execute. Qiskit runtime primitives provide the interface to IBM Quantum hardware that allows transpiled circuits to run. This step also includes using error suppression and mitigation techniques, which can largely be abstracted away from the user. Lastly, we post-process. In this step, the data from the quantum processor itself is processed, providing the user with useful results on the original problem. Basically, this step encompasses any further analysis of the data that is acquired. Now we're ready to discuss the foundation of quantum programs, which are quantum circuits. Hopefully you're already familiar with quantum circuits, but in case you're not, you might want to first check out Lesson 3, Quantum Circuits, which is a part of Understanding Quantum Information and Computation, linked below. We're only going to be giving a short refresher here. Now, a quantum circuit is a network of quantum gates and measurements linked by wires that represent the qubits. Quantum circuits can be read like sheet music from left to right, starting at time 0, which is all the way on the left. Virtual qubits, meaning qubits that haven't yet been assigned to an actual physical qubit on a processor, are listed in increasing order from top to bottom. Once we set up our circuit, we can add gates to it. Single qubit gates, like this Hadamard gate here, affect only the qubit whose wire it's placed on. Multiple qubit gates, like this C0, affect 2 or more qubits linked by the gate. Here in this example, the state of qubit 1 changes depending on what the state of qubit 0 is in. After all of the gates are applied, we can perform measurements, which cause the results to be written onto classical registers. One particularly important characteristic of a circuit is its depth. The depth of a quantum circuit is the minimum number of layers of quantum gates executed in parallel required to complete the computation defined by the circuit. To be clear, quantum gates can be executed in parallel, or in other words, at the exact same time, whenever they don't have any qubits in common. But if 2 or more gates act on the same qubits, then we can't perform them in parallel. We're forced to perform them one after the other. Because quantum gates take time to implement, the depth of a circuit roughly corresponds to the amount of time needed for quantum computers to execute the circuit. So knowing the depth of a circuit is important for knowing that it can be used to run on a particular device or not. It also will tell us if it has a good chance of turning out an accurate result. Next, let's move on to the selection of a quantum processor. IBM has recently released a whole new fleet of processors, all having over 100 qubits, and you can log on to quantum.ibm.com to see which processors you have access to. The processors are all named after birds for reasons, and the different logos represent different types of processors. So for instance, these ones represent eagle processors, and this icon is a heron. The name of the specific processors are also found at the top. They're all named after cities, but that doesn't necessarily mean that the processor is physically located in that city. Those are just names. Qubit count, EPLG, and clops are also factors that are all listed. We'll go over each of these. Qubits. Now this is pretty self-explanatory. Qubits is just the number of total qubits available to use on that sole quantum processor, or QPU. EPLG stands for the errors per layered gate, which measures the average gate process error in a layered chain of 100 qubits. Basically, you want this to be as small as possible. CLOPS stands for circuit layer operations per second, and it measures how many layers of a quantum volume circuit, which is a virtual circuit, a QPU can execute per unit time. The higher the number, the faster we can compute. This is equivalent to what FLOPS means in classical computing. Now, these different metrics may be more or less important depending on the specific application area that you're interested in. Next, let's discuss at a high level mapping to quantum circuits. The first step is the mapping step, which essentially answers the question, how do I translate my problem into a quantum circuit that can be run on quantum hardware? Now, there's no doubt about it. Mapping is a hard problem, and it's an active area of research. Sometimes just being able to take a computational problem and come up with a sequence of quantum gates that help solve it is the hardest part. There isn't a foolproof method that guarantees success, but there are recommended guidelines and examples of problems that we already know how to map. The first guideline is to let classical computers do whatever work that they are better at themselves. Tasks that are easy for classical computers probably won't benefit from a quantum computer. Quantum computers are for problems that are classically hard. Of course, if this is your very first time using Qiskit or a quantum computer, don't worry about finding a problem that is computationally complex. Break it down into smaller problems that you can learn to address before going straight to a utility-scale project. Next, translate the outcomes for your problem that you want to measure or understand into an expectation value problem or a sampling problem. For most types of problems, this essentially corresponds to calculating a cost function. A cost function is a problem-specific function that defines the problem's goal as something to be minimized or maximized, and they can be used to see how well a trial state or solution is performing with respect to that goal. This notion can be applied to various applications in chemistry, machine learning, finance, optimization, and so on. Also, keep in mind that the hardware that you're going to be using has a specific topology. Some qubits aren't connected and some are. And ultimately, you'll need to map your problem to a circuit that represents this. IBM Quantum processors use what's called a heavy hex topology, which essentially equates to qubit connections in a hexagonal lattice, which we'll get into more later in the course. For now, the most important thing to keep in mind is that this stage requires practice. You need to have a good understanding of not only your problem, but also the quantum hardware capabilities. And we'll go through a specific example and use case later on to see how these can be best balanced. Now let's discuss how to optimize a circuit for the hardware that we've selected. The overall goal of the optimization step is to map all of the virtual qubits from our circuit to actual real qubits somewhere on the topology of the processor. The name of the game is to reduce errors as much as possible. To do this, we first need to route and lay out our circuit efficiently. First thing to keep in mind is that not all qubits are connected, as I've already said. Some are actually far away from one another on the chip, so we need to reduce or eliminate long-distance interactions whenever possible. You can apply a sequence of swap gates between neighboring qubits to move qubit information around, but swap gates are costly and prone to errors, so there may be better ways of doing this. Next, layout and routing are iterative processes, and they assign a virtual qubit to your circuit on the physical qubit on the hardware. You can do this by hand, but there are also tools in Qiskit which can make recommendations for the physical qubit layout based on approximate error rates. Next, we can compose sequences of 1-qubit gates acting on the same qubit into single gates. And we can also sometimes get rid of unnecessary gates or combinations of gates. For example, some combinations of gates can be reduced to simpler combinations, and sometimes combinations of gates even equate to just a simple identity operator, so we can simply eliminate them. You can do this automatically using the Qiskit transpiler, or you can do it manually on a gate-by-gate basis if you have a good reason to do so and you want more control. Once we've improved the circuit layout, routing, and gate counts, either by hand or by using the Qiskit transpiler, we usually want to visualize our circuit to make sure that the timing of all the gates makes sense. There is an argument that you can flag in the transpiler to visualize the timeline of your circuit and make sure that everything is lined up the way that you would expect. Now let's talk about error suppression. Error suppression refers to various techniques that transform a circuit during compilation to minimize errors. It's different from error mitigation, which takes place after the circuit has already been run, and we'll come to that shortly. The two most common forms of error suppression that we take advantage of are dynamical decoupling and Pauli twirling. There is going to be some technical details here, but you can always refer back to this later. So the first, dynamical decoupling, is used to effectively cancel out some of the noise affecting the qubit by applying a series of gates that together amount to the identity operation, like XX sequences, and whose net effect is to approximately cancel out the noise channels affecting the qubit. Pauli twirling is a way of inserting random gates to simplify the average noise. The randomness helps prevent the effects from different errors from building up as fast, and also makes the noise easier to characterize. Now, this method also forms the basis of an error mitigation technique, and we're going to be discussing that later. Again, there's a lot of information here, and don't worry if it doesn't all sink in immediately. Luckily, a lot of this can be done automatically using the Qiskit transpiler. Transpilation can be tricky though, but the transpilation is such a crucial step to achieve utility at scale that it requires a lot of trial and error in order to be mastered and obtain the best results. Now I want to take a brief interlude to discuss the Qiskit transpiler and its capabilities a bit more. I'll do this at a very high level, and we'll get into the details and see some examples later on. In general, transpilation is the process of rewriting a given input circuit to match the topology and specific quantum device and optimize the circuit for execution and resilience against noise. It also rewrites a given circuit into the basis gates of that specific quantum processor you have selected to use. Qiskit has 4 built-in transpilation pipelines, and unless you're already familiar with quantum circuit optimization, I definitely recommend using one of those built-in pipelines. By default, the transpiler includes these 6 steps: initialization, layout, routing, translation, optimization, and scheduling. Now, initialization refers to any initial pass that is required before we start embedding the circuit onto the back end. This typically involves unrolling custom instructions and converting the circuit into just 1 and 2 qubit gates. The layout stage applies a layout, mapping the virtual qubits in the circuit to the physical qubits on a backend. Routing runs after a layout has been applied and injects gates, such as swap gates, into the original circuit to make it compatible with the backend's connectivity. The fourth stage is translation. In this stage, the gates in the circuit are translated to the target backend's basis set. Next is optimization. This stage runs the main optimization loop repeatedly until a condition, such as reaching a certain target depth, is met. We have 4 different optimization levels that we are able to choose from. Last is scheduling. This stage is for any hardware-aware scheduling passes. At a high level, scheduling can be thought of as inserting delays into the circuit to account for any idle time on the qubits between the execution of instructions. So like I said, there are 4 optimization levels ranging from 0 to 3, where higher optimization levels take more time and computational effort, but you might end up with a better circuit. Optimization level 0 is intended for device characterization experiments, and as such, only maps the input circuit to the constraints of the target backend. It doesn't perform any optimization. Optimization level 3 spends the most effort to optimize the circuit. However, as many of the optimization techniques in the transpiler are based on heuristics, spending more computational effort doesn't always result in an improvement in the quality of the output circuit. If this is of further interest, please check out the transpiler pages in the Qiskit documentation linked below. Now we are ready to discuss the actual execution of a quantum circuit. The Qiskit runtime primitives provide an interface to IBM Quantum hardware, and they also abstract away error suppression and mitigation from the user. The sampler primitive returns the quasi-probability distribution, or counts, representing the likelihood of measuring certain bit strings, zeros and ones. The estimator primitive returns expectation values of observables corresponding to physical quantities. So in a little bit more detail, the sampler runs the circuit multiple times on a quantum device, performing measurements on each run and constructing the probability distribution from recovering those bit strings. The more runs, or shots, it performs, the more accurate the results will be. But this requires more time, and the quantum resources required to run that. Specifically, it calculates the probability of obtaining each possible standard basis state by measuring the state prepared by the circuit. Qiskit's estimator uses a complex algebraic process to estimate the expectation value on a real quantum device by breaking down the observable into a combination of other observables that have known eigenbases. And running under the hood of the primitives are the techniques called error mitigation. Error mitigation is an umbrella term for all of this, and it basically refers to the techniques that allow us to reduce circuit errors by modeling the device noise at the time of execution. Typically, this results in quantum pre-processing overhead related to the model training and classical post-processing overhead to mitigate errors in the raw results by using a generated model. But in exchange for this overhead, we're able to get much more accurate results. There are multiple techniques that we can implement for error mitigation, and we're going to go over 3 of them in more detail. Be aware, however, that this is an area of active research, so new techniques will likely be invented, and older ones will continue to be improved upon. The resilience level increases the cost, or in other words, the time it takes to run your job. We already said that at resilience level 0, the transpiler doesn't really do anything to your circuit. But starting at resilience level 1, it introduces a method called twirled readout error extinction, or we call it TREX for short. Twirled readout error extinction uses polytwirling to mitigate noise, which is something that we've already touched upon. It's a very general and effective technique that, intuitively speaking, makes the noise less irregular and easier to deal with. Starting at resilience level 2, we introduce zero noise extrapolation, or ZNE for short. This is a popular technique that we've recently had a lot of success with. The idea behind ZNE might be a bit surprising. We actually add additional noise on top of what's already there. But what this does is it allows us to extrapolate in the reverse direction to predict what the results would look like if there was less noise. This can be done in several specific ways. For instance, we can stretch out the gates to make them longer and thus more prone to error, or we can run more gates that ultimately result in an identity operation. So the circuit doesn't actually functionally change, but we purposefully sample more noise. You do have to do this for every circuit and every expectation value that you want to keep track of though, so you can see how it can end up being very expensive in terms of the time required. One specific type of ZNE is called probabilistic error amplification, PEA for short. Once we've learned a noise model for a gate, PEA works by sampling errors from that noise model and deliberately injecting them into the circuit. Like I mentioned, lots of new techniques are continuing to be developed and will hopefully be implemented as we see more and more come into play. There's just one final form of error mitigation that I want to discuss, called probabilistic error cancellation. Instead of being at the 3rd resilience level, PEC is a special capability that you have to manually turn on in Qiskit, because the computational resources needed for it don't scale very well compared to the other error mitigation techniques that we've discussed. You begin by learning about the noise that's affecting your circuit by running noise learning or noise characterization circuits for each unique layer of 2-qubit gates that are in your circuit. These results let you describe the noise in terms of Pauli operators. Once you know these noise terms, you can modify your circuits so that they effectively have the opposite Pauli's built in to cancel these noise channels. In some ways, this process is similar to that of noise-canceling headphones. However, this way of undoing the noise is very costly, with a time to run that grows exponentially quickly in the number of gates, so it may not be the best choice for a very large circuit. We have now reached the final stage, post-processing. In the end, if you've done a good job and employed proper error mitigation techniques, you might see your final answer shift like in this figure. Here, an unmitigated distribution, shown in purple, is quite far from the true expected value shown here by this line. However, once we apply our error mitigation, we obtain a mitigated distribution shown here in blue, which peaks much closer to the true value. Now, this all comes at a cost, and here we can see that the variance, or the width of the distribution, is increased, which isn't generally what you want, but everything comes at a cost. Luckily, we can account for this by running more shots, which causes the distribution to shrink back to an acceptable level of uncertainty. So that's about it for this lesson. For next time, we're going to take all of these steps and put them together and work through an area and an example of actual application interest. There's a few things that I can recommend that we do until then. If you haven't yet, make sure that you download and set up Qiskit 1.0. You can also check out the associated lesson for this chapter and the previous episode in the IBM Quantum Learning platform. And lastly, if you have any interest in digging in more and learning more about error mitigation techniques, check out one of the numerous sources that I've linked below. Until then, we'll see you next time.